Hello everyone, my name is Felipe Polo and I'm a master's student at the University of São Paulo in Brazil. I'm very happy to present our work covering cheap adaptation in high-dimensional and divergent distributions. So this presentation was based on the full paper that can be found on this link. So let's briefly give a background of our problem. Essentially, we are working within the framework of domain adaptation, in which we have different distributions for training and testing. More specifically, we are working within the Covariate shift adaptation framework, where the joint distributions of features and labels are different only by the marginal distribution of features. Moreover, we cannot sample the labels from the test distribution. Covariate shift adaptation is usually corrected using importance weighting, which is an idea very similar to importance sampling. One problem with that approach is that it fails in high-dimensional settings due to small effective sample sizes, leading to poor performing models in practice. Let's briefly present the importance weighting method that is traditionally used to perform covariate shift adaptation. So our main objective is to minimize a risk function that, which is the expected value taking with respect to the test distribution P. Using some algebraic manipulation, we can rewrite that risk function in terms of the train distribution Q. And we ended up having a weighted version for the risk function, which translates into a weighted version for the regularized empirical risk, which we want to minimize in practice. Our paper has two main contributions, which are a new theoretical connection between effective sample sizes, high-dimensional settings, and generalization bounds in the context of covariate shift adaptation, a simple, general, and theoretically sound approach to combine feature selection and covariate shift adaptation. So let's talk about our first contribution. So assuming the weighting function we use is proportional to a density ratio P over Q, then we can show the following relationships, and also assuming this formulation for the effective sample size. So our main idea is that higher dimensions leads to a higher divergence between Q and P, which is equivalent to a lower effective sample size and a worse generalization. So in our paper, we showed that those relations are valid under some conditions. Our second contribution regards a feature selection procedure for covariate shift adaptation. Our approach is theoretically supported by the concepts of sufficient dimensionality reduction and mutual information. Our idea can be summarized in the diagram below. So, making feature selection via SDR implies in a higher effective sample size, but also implies that the best case scenario results are kept. And everything tends to lead to a better performing models in practice. So in our paper, we have conducted some experiments as well, and we used some popular data sets to conduct 20 regression and classification experiments. And in our approach yields to good performance with improved effective sample size compared to other benchmarks. So we had the best results. And for more details, please talk to me during the poster session or take a look at your paper at its full version. Thank you very much.